So hello. Okay, please hold on. Okay. Okay. Good day. We will continue with our chapter number two, part number three, on fundamentals of mechanics. So we will covering this for EMG 36404, electrical machines and power system. Okay, we can see that for mechanical part, there are various things that we need to calculate in order for us to do the analysis. Okay, the first thing that we need to calculate, that commonly we calculate, is the force. So force equals to F equals to ma. Okay, F equals to ma is actually representing the force of the body. Okay, within a 30 kilometers radius close to the surface of the earth. Okay, which we experiencing a gravity of acceleration 9.81. Okay, so we know m equals to mass, so mass in a kilogram. Okay, and F equals to the force of gravity acting on the body, which is on Newton. Okay, another thing that we can see is the torque. So torque is produced when a force exerts a twisting action on a body. So meaning, so there's a body, and because of the force applied, the body started to rotate. So that is what we call it as a torque. So torque can be calculated with this formula: T torque equals to force times radius. Okay, so torque will be in Newton meter. So F equals to in will be in Newton, and R will be in meter. Okay, so torque is equal to the product of force times with the perpendicular distance between the axis of rotation and the point of application of the force. Okay, so it's perpendicular. Okay, so we will see one example. So example one, a motor developed a starting torque of 150 Newton meter. Okay, so if a pulley of the shaft had a diameter of 1 meter, okay, determine the braking force needed to prevent the motor from turning. So we already can see here torque is given. Okay, and the diameter is given, so we can find the radius. So 1 divided by 2, so 0.5 meter, and we need to find the braking force. So the radius is 0.5 meter. The braking force F equals to T over R, where we can get this formula. This is from this formula. We just rearrange. Okay, so this R bring to down, so we can find the F equals to T over R. So torque is under 50 Newton meter, R is 0.5 meters, and when you solve it, you get 300 newtons. Okay, so another thing that we always will use is the mechanical work. Okay, mechanical work done. Okay, so mechanical work is done whenever a force F moves in a distance. So we can see here, so force is moving this direction at the distance of D, that it is released. So meaning a mechanical work is done. Okay, so the formula for mechanical work done is W equals to Fd. So F is the force in Newton, D is the distance of the force in meter. Okay, so we can see one example. A mass of 50 kilogram is lifted to height of 10 meters. So from here is lifted here. So we know. So that's a distance d of 10 meters, and we know there's a force acting. So which is 50 times 9.8 k in Newton. Okay, for 50 kilogram. So we can determine the work done. So the force of gravity acting on 50 kilogram mass is F equals to ma. So 50 times 9.8 equals to 490 Newton. and the work done is W equals to Ft. So F is 490 Newton and D is 10 meters. Okay, so the work done is 490 Newton times 10 meters, so which is 4900 joule. Okay, for the power is the rate of doing work. It is given by the equation. Okay, so it's given by the equation here. So power is the rate of doing work. So earlier we have seen the work done. Okay, so that's the amount. So this is the rate. Rate is always related to time. So how much work is done in 1 minute? How much work is done in 1 second? So that is what we want to calculate. So it is actually the power that is used or generated. Okay, so the formula for power is P equals to work done divided by time. Okay, so you can see here, so work is done. So the person is throwing, force is used, and is covering the distance, and for it to reach here, it has a time. Okay, so as an example. Okay, so we can see one example. An electric motor lifts a mass of 500 kilogram through a height of 30 meters in 12 seconds. So meaning from here, you lift to here in 30 meters in 12 seconds for it to run. Okay, and the weight is 500 kilogram. So determine the power developed by the motors, and it already mentioned we need to determine in kilowatt. Okay, so we see the solution. So we know the formula P equals to W over T. So W we know W is Fd. So we can use either this or this formula. Okay. So let's say we want to calculate based on the information for the kilogram is given. Okay. So we know F equals to MA. So M is 500, A is 9.8. So F equals to 4900 Newton. Okay, that once you find the F, we can find the work done. So the work done, W equals to FD. So W equals to 4900 from here times with 30 meters covered. So the work done is under 47,000 joule. Okay, now we can find the power. Power equals to W over T. So W is under 47,000. So T is 12 seconds. So we want to find for 1 second. So you divide by 12. So we know the power is 12,250 watt. So the question asks us to find in kilowatt. Okay, so you divide by 1000, so you get 12.25 kilowatt. Okay, so power of motor. The mechanical power output of a motor depends upon its rotational speed and the torque it develops. Okay, so when we are choosing a motor, we need to know the power of the motor. So we always will have the power in input and also output. So and the power output depends on rotational speed and also torque it develops. Because when we want to choose a motor, we need to make sure the motor has enough rotational speed and also torque. Because if we buy a motor, so let's say for power window in a car, so the motor that is rotating inside must be able to bring the window up or down. It must have enough torque to rotate and bring it up, bring it down or up. Okay, so torque is very important. Okay, in order to calculate the power of motor, so we can use this formula P equals to NT over 9.55. Okay, so P is mechanical power in watt. So T is torque in Newton meter. N is the speed of rotation or revolution per minute. Okay, and 9.55 is a constant to take care of the units. So this is actually 30 over pi. So 30 over 3.142. So you get 9.55. Okay, so example 4. So during a pronic brake test on an electrical motor, the spring scales indicates 25 Newton and 5 Newton respectively. Determine the power output if the motor turns at 1700 RPM and the radius of the pulley is 0.1 meter. So we can see, so the radius is 0.1. So n is given 1700 revolution per minute. So we can see there are two spring scales. So this P1 is actually calculating downward force, and this P2 is calculating the upward force. So it will cancel each other. So we can find the differential in order to calculate. So we want to determine the power output. So to solve, T equals to FR. So we use this formula. F we know, 25 minus 5. We want to find the differential. Okay, 25 minus 5 Newton. So R is 0.1. Okay, so we get 2 Newton meters. Okay, 2 Newton meters. So the power is P equals to NT over 9.55. So the previous formula. So we know N is 1700, T is the torque, 2 Newton meters. So all the informations are there. So the 1700 times 2 over 9.55. So we get the power equals to 356 watt. Okay. So in order for us to buy a motor or electrical machine, we need to know the efficiency of the machine. Because if we buy something, it will constantly giving you loss. So it is not profitable for any agency or company. So later on, when we work as a engineer, we need to ensure that the machine we are generating or producing or buying, it must have the efficiency, which is easy to maintain and also fulfill the need of the company. Okay, so in order for that, so we can calculate the efficiency of the machine. Okay, the efficiency of the machine is given by this formula. So nu equals to PO over PI times 100. Okay, so efficiency always we get it in a percentage. Okay, nu. Okay, so P0 is output power of the machine. Okay, so the machine always have output and input power. So the input is going into the machine, output is the one that we are getting. Okay, so the output. Okay, so we need to have the efficiency, we need to calculate the ratio, and we convert it into percentage. So we see an example. Okay, so that's an example for this. Okay, so a under 50 kilowatt electrical motor has an efficiency of 92%. Okay, 92%. So 92% efficient, so 8% inefficient. So that is the meaning. So when it operates at a full load. Okay, so determine the losses in the machine. So we want to find out the amount of the 8%, the remaining 8%. Okay, so how to solve? So 150 kilowatt is referring to the mechanical power. Okay, the mechanical power output. So this is actually 150 kilowatt is actually PO of the motor, because you say it operates. Okay, meaning it's giving output. Okay, so we can use the same formula. So we are not having times 100 here because we incorporate inside. Okay, so the efficiency equals to nu equals to P0 over Pi So we rearrange this formula because we want to find the pi. So we just rearrange this formula. We can get this formula pi equals to p0 over nu. Okay, p0 is 150 divided by 92 over 100 or 0.92. Okay, so pi is 163 kilowatt. So the mechanical output power is P0 150 is given. So the loss is Pi minus P0. So highest number minus the lowest number. So 163 minus 150. So we have 13 kilowatt of power loss. Okay, so that is how we can calculate. Okay, kinetic energy of the linear motion. Okay, so when we are dealing with anything, so anything that is moving, we know that it has a kinetic energy. And because kinetic energy is related to velocity. Okay, we can have a kinetic energy in linear motion, and we also have a kinetic energy in a rotational motion. Okay, so both having a different formula. So let's say a stone is falling or the ball is falling. You can see as it goes down, so the velocity increase, the kinetic energy increase. So same height, but it is dropping further. So you can see this kinetic energy is more than this kinetic energy. So similar. Okay, so it's related to gravity as well. Okay, so EK, so EK is kinetic energy. So we measure in joule. M is the mass in kilogram, and V equals is the speed of the body in meter per second. Okay, so we can use this formula to calculate the kinetic energy of the linear motion. So we see an example for this. Okay, so a bus having a mass of 6,000 kilogram move at the speed of 100 kilometer per hour. If it carries 40 passengers having a total mass of 2,400 kilogram, determine the total kinetic energy of the loaded vehicle. So we want to find the kinetic energy of the loaded vehicle. So the mass of the loaded bus. So we need to add the weight, the mass of the bus, and also the mass of the passengers. So 6,000 is the mass of the bus. So 2,400 is the mass of the passengers. Okay, so the mass m equals to 8,400 kilogram. Okay, the speed is given, it's moving at 100 kilometer per hour, but we want to find it in meter per second. So what we need to do, so kilometer we convert it to meter first. So 100 times with 1,000. So divide by h. H is, so in 1 hour we have 3,600 seconds. So when we solve it, we can get the answer in meter per second. So 27.8 meter per second. Okay, we already find m, we already found v, and now we can find the kinetic energy. So we use this formula, Ek equals to half mv square. So half times m is 8,400, v is 27.8. So you need to square it. Okay, you solve it, you get 3.25 million joule. Okay, as an answer. Okay, so earlier we have seen the kinetic energy for the linear motion. So now we see for rotational motion, rotation. So we call it as a moment of inertia. A revolving body, so revolving meaning it's a rotating body. So it also possesses a kinetic energy. So whenever there's a movement, so we have a kinetic energy. Okay, is the magnitude. So meaning the value of kinetic energy depends on the speed of rotation, how speed it rotates, and also the mass and the shape of the body. Okay, for kinetic energy of the rotation, so we have calculated. So Ek equals to 5.48 times 10 to the power of -3 J n square. Okay, so this is the formula. So if in your exam or test is given is a rotational uh, kinetic energy, so straight away use this formula. Okay, so we can see Ek is kinetic energy in joule. So J is the moment of inertia, so kilogram a meter square. So and n is the rotational speed, revolution per minute. Okay, and 5.48 times 10 to the power of negative 3 is a constant. So the derived from pi square. So pi is 3.142 times square divided by 1800. You will get this value. Okay, so one more subtopic, the torque, inertia, and the change in speed. So the rate of change of speed, okay, depends upon inertia and torque. Okay, so we know the speed. So speed is changing, and the rate of the change is depends on the inertia and the torque. So we can calculate. So change in speed, revolution per minute, so equals to 9.55 times t times changes in time divided by the moment of inertia. Okay. So moment of inertia is a bit special for us to calculate. So moment of inertia, we always call it J. So around the axis of rotation. So we want to see where is the axis of rotation and the shape of the body. Okay, so case one. So if the mass is a distance r from the axis of rotation, we use this formula J equals to mr square. So if we are dealing with a solid disk or solid body and with the center r, radius r, we use this formula J equals to mr square over 2. Okay, so this is one formula for us to use. And if it is a annular ring, so ring like this, so meaning there's a mass here, and in between is hollow with two radius and the center of mass, center of rotation. We can use this formula J equals to m over 2 r1 square plus r2 square. And if it is a straight bar like this, straight bar, you can have two conditions. One, the axis of rotation is in the middle of the bar, so meaning the bar is rotating at the axis. Then we can use J equals to ml square over 2. And if the bar is having an outside axis of rotation, so we need to calculate the R1 and R2 for us to replace in this formula. J equals to m over 2 r1 square plus r2 square plus r1 r2. So this is already derived for you to use. So you'll see one example. Okay, so when the question comes, we need to see which formula to take based on the body of the test material. So let's say you want to test it on a solid body, then we use this. It's a solid disk. Okay, if we are dealing with the hollow ring, then you use this formula. So if we are using a mass in this setup, then use this formula. So we no need to memorize everything. So we just need to know which one to use. Okay, so usually it will be given during the exam, and you need to know which one to select and use. Okay, like in this case, so we have a solid solid of 1400 kilograms steel flywheel with a diameter of 1 meter. So radius is 0.5 meters and thickness of 2 to 5 millimeters. Okay. So we need to determine the moment of inertia and the kinetic energy when the flywheel revolves at 1800 revolution per minute. Okay, so most of the details are given. So solution, first we want to find the moment of inertia. So moment of inertia J, so we know it's a solid body. So here the question is given in 3D. So we need to convert it into 2D for us to understand. So when we see this, we know it's a solid body, center axis of rotation at the middle, and it has a radius. Then we can find. So we can refer to the previous one. So since it fulfills this, just take this formula. J equals to mr square over. So J equals to mr square over 2. So m is 1400 kilogram. R is 0.5 square over 2. So we solve it. We know we get the moment of inertia J equals to 175 kilogram meter square. Okay, so moment of inertia already defined. Now we need to find the kinetic energy, because the question asks to find the kinetic energy when the RPM is 1800. Okay, kinetic energy KE or EK equals to 5.48 times 10 to the power of negative 3 Jn square. Where you get this formula? From the previous slide. This one. Okay, so for us to find the kinetic energy. Okay, so you replace the value. J we already found. So 5.48 times 10 to the power of negative 3 times 175 times with n square is 1800. So it's coming from the question. 1800 revolution per minute. Okay, so the kinetic energy is 3.1 megajoule. Okay, so last example for today. A flywheel having the shape given in the figure composed of a ring supported by a rectangular arc. The ring and arc respectively having a mass of 80 kg and 20 kg. So determine the moment of inertia of the flywheel. So you can see, so it has a hollow ring and it has a bar in between, and this is the center of rotation for both. So diameters all given, so we can calculate the moment of inertia. Okay, for this case, so we need to deal it separately. First we do analysis for the hollow ring, and second we do analysis for the bar, okay, or the hub. Okay, so for the ring, so we know it's a ring with anti-hollow, so we just take this formula. Okay, so J equals to m over 2 r1 square plus r2 square. Okay, we just apply this formula. Okay, so only one J, so J1, so just cancel one more. So J1 equals to m over 2 r1 square plus r2 square. So m is 80 given here, so 80 over 2. So R1 is from here, so 0.4 square plus 0.3 square. So when you solve it, you get 10 kilogram meter square. Okay, so that is for the ring. Second, we go for the hub. Okay, so this is the diagram. Okay, so for this we check the table. So straight bar, so this is the diagram, so we just take this J equals to ml square over 12. Okay, so J2 equals to ml square over 12. So M is 20 given in the question. L is 0.6, so 0.6. So same, this one also same distance. Okay, square over 12. So you solve it, you get 0.6 kilogram meter square. So question asks to determine the moment of inertia of the flywheel. So meaning we need to calculate the total. The total is J1 plus J2. So 10 plus 0.6 is 10.6 kilogram meter square. Okay. So with this, so we came to the end of our lecture today. So if you have any questions, so you may ask me anytime. Thank you.